Today we'll continue our discussion of understanding motion in multiparticle systems using the concept of potential energy as part of the energy principle. Using the gravitational potential energy as a specific example, we'll discuss some general properties of potential energies. At the same time, we'll show how to draw energy graphs, which are very useful tools to help us understand motion in energy terms. Let's start with the multiparticle system shown with two particles interacting gravitationally with no interactions with the surroundings. Here's a warm-up question. What would the graph of the gravitational potential energy as a function of separation distance r look like? Here's what u sub g looks like, correctly plotted as a function of r. It might strike you as weird that the potential energy is always negative. Let's explore this to see if it makes physical sense. First, let's write down the general form for our energy principle here for this situation. The change in total energy is equal to the change in the total kinetic energy plus the change in gravitational potential energy. And that must be equal to 0 since in this example there is no transfer of energy between the system and the surroundings. Here we remember that delta K total is just the sum of the kinetic energy changes for each particle in the system. Notice what shows up directly in the energy principle is the change in the value of the potential energy, here, delta U sub g, not the value itself. So, potential energies could be positive or negative as long as the change in the potential energy makes physical sense. This is a general property of potential energies. Let's go a little further and expand out these changes in terms of the usual final minus initial form. Now we can do a little algebra, and we can rearrange it into this form, putting all the final energies on one side of the equation and the initial energies on the other side of the equation. This is still the exact same energy principle for our system, and what we see is that the statement that the sum of the changes equals 0 is equivalent to saying the total energy E is constant. Now let's imagine our drawing here is the final state, and in our initial state, the particles started out very, very far apart. Meaning the separation r between the two particles is very, very large. What is u sub g in the final state? Well, in our expression for u sub g, we see a large r means a large denominator, which means u sub g is small. Nearly 0 if r is very, very large. This makes physical sense because when the particles are very far apart, the gravitational interaction should be very, very weak, meaning the total energy of our combined system should be just due to the kinetic energies of each particle added together. Very weak interaction means the potential energy is nearly 0. This is a general property of potential energies, not just gravitational. When an interaction becomes very weak, in this case by having the particles very far apart, the corresponding potential energy is nearly 0. Now the initial state shown here looks very like the binary star example we discussed in the lecture when we introduced the gravitational potential energy. Recall from that example that, starting from far apart, the stars were drawn together by their mutual gravitational attraction to a final state that looks something like the final state we see here. Recall also in that example that the energy principle told us that the stars gained kinetic energy, and that energy came from the decrease of potential energy as the stars moved closer together. Here's yet one more general property of potential energies. If the interaction is attractive and depends upon the separation of the individual parts or particles in the system, then the potential energy decreases as the particles get closer together. Graphically, this change in the gravitational potential energy, this decrease, looks like this. And in this figure, we can now see why the gravitational potential energy is always negative. First, by the general property that potential energies must approach 0 when interactions are weak, we see that the gravitational interaction is weak at large r. So, u sub g is nearly 0 at large r. Second, since the gravitational interaction is attractive and the potential energies for attractive interactions decrease as particles get closer together, therefore gravitational potential energy must decrease from zero, that is, go negative, as the separation between the particles decreases. Here's a clicker question where these ideas are applied in a little different context. Give this a try. Here we once again have an attractive interaction. In this case, the gravitational interaction between the comet and the star. And we are told the separation distance is increasing. Thus, for the comet plus star system, the potential energy must increase, become less negative as r increases. Now, the total energy of the star plus comet system is constant since there are no energy transfers between the system and the surroundings. And the total energy must be equal to the sum of the kinetic and potential energies. So, if the potential energy increases, the kinetic energy must decrease. Now, to this point, we see that this kind of graph, called an energy graph, helps us visualize the meaning of potential energies. But we can use the energy graph to visualize other energies as well. Let's see how this works. Let's consider another concrete example of a two-particle system. Let's take Object 1 to be a planet of mass m1 and Object 2 to be a spacecraft of mass m2. Let's say that in this initial state the planet is at rest and the spacecraft has some kinetic energy, k sub s. Here's the question we're going to answer. From an energy standpoint, under what conditions will the spacecraft escape the planet? Escape here means the spacecraft will be able to achieve an arbitrarily large separation distance r from the planet. The energy principle tells us that for the planet plus spacecraft system, with no external interactions, the change in the total energy is zero, or equivalently, the total energy of this system is a constant. We can plot that easily, except here we have to say something about that constant. It can be positive, negative, or zero. Let's consider each of these cases in turn. First, let's say E is a positive constant, and we plot it that way. Now we know the total energy is equal to the sum of the system kinetic energy and the potential energy. And moreover, we know what the potential energy looks like as a function of separation. So from this, we can obtain the system kinetic energy, since we know that the total kinetic energy must be the total energy minus the potential energy. You can visualize doing this subtraction at each value of r, something like this. So what do we learn from this graph? Well, if we key in on the kinetic energy, we first remind ourselves that this is the total kinetic energy of both the planet and the spacecraft. However, in this case, with the planet initially at rest and the very large mass differences between the planet and the spacecraft, the interaction will hardly affect the kinetic energy of the planet. So all the changes in potential energy will show up as changes in kinetic energy of the spacecraft. So we can write that k sub s, the spacecraft's kinetic energy, is, to a good approximation, the total kinetic energy here. Now, we notice that the spacecraft has kinetic energy for all values of separation, meaning that the spacecraft always has some non-zero speed, and so it is possible for the spacecraft to always further increase that separation from the planet. This means for E positive, the spacecraft can escape. This is an example of what we call unbounded motion. The spacecraft's motion relative to the planet is not restricted. Now let's look at the case where E is negative. Again, we can sketch the total energy E, and from that sketch, find the kinetic energy. But notice here a big difference from the positive total energy case. The kinetic energy goes to zero at a finite value of r. This means that there is a maximum separation distance that cannot be exceeded. This is so because at that maximum separation r, the spacecraft's kinetic energy is zero. The spacecraft can't move any further away. This is an example of bounded motion. The spacecraft's motion relative to the planet is restricted to a limited range of separation distances. The final case is E, the total energy, equal to zero. What does the energy graph for that look like? And what will the motion be, bounded or unbounded? Try to sketch the energy graph for this case, and then see if you can answer this clicker question. Here's what the energy graph should look like for the total energy E equal to zero. This is also a case where the spacecraft's motion is unbounded. We see from the graph that the spacecraft will have non-zero kinetic energy for any finite value of r. The kinetic energy of the craft goes to zero only as r goes to infinity. The case of E equals zero is the minimum energy case whereby the spacecraft can escape. Now, as a final comment for this lecture, we emphasize that the energy graphs don't tell us specifically what the trajectory of the spacecraft is in any of these cases. For each case, E, the total energy, positive, negative, or zero, there are many possible different trajectories. This is due to the scalar nature of energy, which typically doesn't give us information about the direction of motion, which we would need to specify the spatial path of a moving object.